Yeah, it won't be
I was here. Okay, let's start. Adam is an outstanding student, so in fact he has beaten all the records we've had in our lab. So he has written 4 first author papers, 4 other papers to which he contributed. 2 chapters of his PhD can be converted into 2 additional first author papers with minimal tweaking by me. So it's a very impressive record. And
all right, well, thanks for the introduction. As mentioned, I'm talking about high resolution mass spectrometry. I've omitted it from the title because it's long enough as it is. And the idea is chemical composition and photochemical evolution of biogenic secondary organic aerosols. It's work done with Sergey, who did introduce himself here at UCI, and in collaboration with Dr. Alex and Dr. Julia Laskin at the Environmental Molecular Sciences Laboratory at Pacific Northwest. Okay, so I've mentioned the term a couple times. For those that don't know, what is an aerosol? Start off. So definition is a stable suspension of solid or liquid particles in a gas. So here's kind of a cartoon where this kind of greenish color is the gas molecules and these bigger circles are particles. And then the whole thing is termed aerosol. The particles, we call them many different things. Particles, aerosol particle, or particulate matter will probably all come out of my mouth during this talk. I'm all talking about the same stuff, this stable suspension of solid or liquid molecules. Typical sizes, so for an atmospheric chemist or atmospheric particle chemist, a rock, a very large particle is about 10 microns. And then they go down from there. Coarse is 2.5 to 10, fine and ultrafine, very small in the nanometer scales. So why study particles? There's 3 main reasons. Health effects is a very big one. So this was 1993 New England Journal of Medicine found an association between air pollution and mortality in 6 US cities. They've since done many, many more associations and work after this. This was kind of the first one. So here's then the plot that they found where as the concentration of particles goes up, the rate of mortality increases. Right? So you study. So to do this, we're an experimental group, so we generate aerosol in our lab. So here is a picture of our aerosol chamber in our lab. It's a very large Teflon bag, so 5 meter cubed, about 5,000 liters. We inject our limonene and our ozone, we create our particles, we let them react for an hour or so in the bag, and then collect them either by filter or an impactor collection. There's also a whole suite of instruments and particle sizers and things that I'm not going to go into in too much detail, but we have. So another way, this is our our more sophisticated reaction cell, biomass burning aerosol. I had to put this in there. So we had this fun study where we wanted to look at a different kind of aerosol and see how our technique stood up against it. So we went out to Roland Hall and lit some pine needles on fire. And here's just kind of an image of a filter collection. So we pull the air through a filter, the particles, very fine mesh filter, particles get stuck on the filter, whereas the gas flows through. And then we extract it. Pull into liquid sampler. This is a very sophisticated impactor. So in impaction, we deal with, as I showed in that one picture, the particles are very large, gas molecules are small. So in an impactor, you have a surface and you shoot your aerosol at the surface and your particles hit the surface and stick where the gas flows around. So the faster you flow, the smaller of a particle you can get to stick on your surface. So this thing works in a unique way where first we grow the particles with water, so we have very large droplets, and then we hit them on a vertical surface which has a flow of water running down and around it that then collects the impacted particles and goes through some pumps and into the vials. So we put in an aerosol flow and we get out a vial with our extracted aerosol all in. Traditionally it's been used with ion chromatography, measuring inorganic ions. More recently they've started measuring total organic carbon, and then very recently, we've started using it with ESIMS to measure the speciated water-soluble organic carbon. And then the final statement, just to leave you with, is that organic aerosols are a very complex mixture, and that evolve within hours due to the interaction with solar radiation. So when they first come off and are emitted, they can definitely be changed. And then this year, we're smaller, but we're stronger. We do all the same amount of work. We just not enough time to play. And of course, the special thanks to all my advisors. Sergey has been just an amazing advisor. You are not the PhD comics advisor. He's too mean. And of course, Alex and Julia, thank you very much for all their help. They've been amazing and helped me so many ways. So with that, one more picture with no chemistry.
So at this point in the process, you're welcome to ask questions.
So you showed a fairly large reaction chamber at the beginning. Does it simulate real-world conditions to do such a large volume?
Yeah, I mean, obviously, the atmosphere is the best reactor. I mean, it's the best place to find atmospheric chemistry. And you know, we started off with very smaller bags, and it really you get a lot of effects from the walls. You know, your particles get lost in the walls, and you can't keep them in there very long. Your chemistry changes. So the bigger the chamber you have, you get less wall effects, and you can also get smaller and smaller concentrations. So in a small bag, you have to use really high concentrations, which aren't really applicable to the atmosphere. And so as you get larger, you can use very small concentrations and still collect enough material. That's really the issue. Yeah?
Yeah, so very, very nicely done, really nicely done, both in the thesis and the presentation. So a question that sort of goes to this issue, I'm sure you know Paul Siemens' work where he has talked about any chamber doing organics. The chamber walls take up organics and they come back to haunt you.
Yeah.
And so do you have any evidence that you may have some contributions from things coming back off the wall that may be more aged, for example, than you expected in the first place? Or have you thought about it?
Yeah, we definitely thought about it. So with the small bags, we change them quite frequently. You know, we'd get a new bag all the time. With the bigger bags,
we saw the Teflon roll going down.
Yeah, that's right. The bigger bag, you know, I would say the only type of evidence I could probably see is when we use the AMS, and you know, you can see, you know, we're putting in isoprene or we're putting in limonene and ozone, and you get some nitrate signal off from the AMS. So you know, there's none in there, but you know, we have put nitrogen in there, and so it could be on the walls. But there's you know, the amounts that could be collected are so small that we wouldn't see it with the ESIMS per se, but it's possible there. Yeah.
So I know what limonene smells like, and I know what pinene smells like. Did you ever smell any of these processed aerosols?
Yeah, I did. I wasn't supposed to, but
Where's Roma?
I'll say that the few I did accidentally smell. So we would extract it, and then you know, a lot of them we would have to cut up to get into the small solvent vial. So we cut up our filters. So yeah, you would be over it and smelling. And yeah, they smelled pretty good. I would say the best smelling one was isoprene SOA. I mean, that stuff is like very fragrant, very, very nice smelling. But there's a lot of things in there that you shouldn't be smelling. It was, but it smelled good.